here we go. Our last section of Chapter 5 is going to blend some material from Section 4.5. The reason for that is because this section is on inequalities. So we can't have really a discussion on zeros without bringing in inequalities. And the reason for that is because the zeros of a graph help us to separate the graph into those that are above the x-axis, into parts that are above the x-axis and parts that are below the x-axis. Now, what information is valuable about those parts that are either above or below is what helps us to solve inequalities involving polynomial or rational functions. Now, on this graph, there are 3 zeros. We have what appears to be a negative 0, a 0 at the origin, and a positive 0. And if you're not a 0 on this function, you're either going to be a positive number or a negative number. For instance, this part of the function's graph consists of y values that are all negative. In other words, this would be a part of the graph that would help us solve an inequality of this format, f of x is less than 0. The piece that's between the negative 0 and the origin would consist of y values that are all positive. And for this reason, this part of the graph would help us solve the inequality f of x is greater than 0. We have another piece for which it goes underneath the x-axis, and that's between the last 2 zeros. And this piece of the function would help us solve the inequality f of x is less than 0 as well. And last but not least, that part of the graph of the function would be an additional piece that helps us solve f of x is greater than 0. On the next page, there's going to be an algebraic way of solving these inequalities. But understand that geometrically, we're trying to find the pieces of the graph that are above or below the x-axis. Now, part of the technique is going to involve a number line in which the x values that make the function positive will be marked by a bunch of plus signs, and the x values that make the function negative will be marked by a bunch of minus signs. So just kind of keep this in mind when we get to that point. With the first part of the graph that's underneath the x-axis, all of these x values going from negative infinity up to that 0 would help us solve the inequality f of x is less than 0. All the x values between the last 2 zeros would help us solve the inequality f of x is less than 0 as well. And I'm putting all these minus signs above those 2 sections of the x-axis because these x values give us negative y values. And in a similar vein, all these x values between the first 2 zeros and all the x values after the last 0 will make our function values positive. Okay, so the zeros help us to separate out which x values give us positive y values and which x values give us negative y values. So we're going to start out with a couple of graphs in which we're going to solve inequalities with. And our first graph is a polynomial. Our second graph is a rational function. Now let's start with our polynomial graph. As you can see, this graph has 3 zeros. We have a 0 of -1, a 0 of +1, and a 0 of +2. When trying to solve an inequality such as f of x is greater than or equal to 0, the greater than symbol can be akin to the word above. And the number 0 itself will be representative of the x-axis. So taken together, greater than or equal to 0 in a graphical context means that we're to look for the parts of the graph that are above the x-axis. Now, how many parts of our polynomial graph are above the x-axis? We've got this part right here, and then we also have this little hill. So much like when we were doing increasing, decreasing problems, if we can identify the parts, then that's kind of like getting us halfway there. The second half is pinning down the parts of the x-axis that correspond to these two pieces. So for the first piece, or the piece that's in quadrant 2, all the x values that correspond to it go from negative infinity all the way up to -1. So we're going to have to use interval notation to express our answer, parentheses negative infinity, comma -1. And notice that there's a bar underneath the inequality symbol, which means that we can include the 0 value of -1. So I'm going to bracket that. What other x values would help us solve this inequality? You guys still with me? So how about the x values between 1 and 2? And again, we can include those zeros of 1 and 2 because of the bar. Now, for part B, we want to solve the inequality f of x is less than 0. In the context of graphs, less than will mean under or below, and then the number 0 will still represent the x-axis. So if we're using a graph to solve this inequality, we want to look for the parts that are underneath the x-axis. And it looks like we have two parts. We have the part from -1 to 1 and the part from 2 to positive infinity. So the x values that correspond to the first part go from -1 to 1. Now, should we use parentheses or brackets on these values? We'll take a peek at the inequality symbol. So the inequality symbol doesn't have a bar this time, so we'll use parentheses. And then we're going to union this with the x values that go from 2 to positive infinity. Okay, any questions about that? All right. So our second graph is a screenshot, the graph of a rational function. And I want to add some detail to it. It looks like there's a vertical asymptote at x equals -2, and possibly one at x equals +1. And it also appears as though the x-axis is serving as a horizontal asymptote, so y equals 0. And let's just assume for simplicity that this end of the branch gets close to the x-axis but never crosses or touches it, as well as the end of the first branch that's on the left. So in other words, this graph does not intersect the x-axis whatsoever. So that means there are no zeros, but that doesn't stop us from being able to answer inequalities using this graph. For instance, in part A, they want us to solve the inequality f of x is greater than 0. Now again, in the context of graphs, greater than will mean above, and then 0 will mean the x-axis. Now, are there any pieces of this graph that are above the x-axis? If so, how many pieces? You got 2 pieces. Yep, we got this piece that's in quadrant 2, and we got this piece that's in quadrant 1. Now the x values that correspond to the first piece are going to go from negative infinity all the way up to negative 2. Now since negative 2 is a vertical asymptote, we'll always put a parenthesis on it, regardless of if there's a bar or not. And likewise, we're going to put a parenthesis on 1 and shade all the way down to positive infinity, because those would be the x values that correspond to the piece that's in quadrant 1. So our interval notation from this will be negative infinity to negative 2, union 1 to positive infinity. And this would be the same solution even if you were to have a bar underneath the inequality symbol. And the reason for that is because negative 2 and positive 1 are each a vertical asymptote. Okay, so just wanted to point that out. Even if there's a bar underneath the inequality symbol, if the x value is for a vertical asymptote, we still use a parenthesis, and that's because it causes division by 0. So I'm going to give you folks a moment to solve part B, where we want to solve f of x is less than 0. So the less than symbol will mean under, and then 0 will mean x-axis. And we do have a piece of the graph that is under the x-axis. It's trapped between the two vertical asymptotes. And the x values that correspond to it are those between negative 2 and positive 1. All right, is that what you came up with? Woohoo! All right, so the next topic is going to be more of an algebraic approach to solving inequalities with polynomials and rational functions. This is something that I refer to as the test point method. And if you've worked with inequalities like this before, say like in Math 113 or different math class with similar topics, you've probably done a sign chart method. A test point method is very similar to it, but I think in my opinion, it's just a little more transparent as to how we arrive at our answers. So I tend to opt for this method versus the other. So if you've never seen it before, you'll have to let me know how you like it. So it is a step-by-step process, and after a couple, it's generally, I wouldn't say second nature, but generally you pick up on it quite fast. The first step is to make sure that one side of the inequality is 0. And once we have one side as being 0, the other side can be defined as our function f of x. But I typically hold off on that until we have like a factored form version of the function. And once we do, that's when I call it my official f of x. Now, if f of x is a polynomial, then what we want to do is find the polynomial zeros. If the function is a rational function, we have to find the zeros and the vertical asymptotes. And regardless of which type of function we have, we're going to use the values we get from either step 2 or step 3 to split up the real number line. And so basically, we're plotting those x-intercepts just from a numerical standpoint versus a graphical. And then what we do is we test a random point from each section of the number line that is split up by plotting these zeros. Okay, that's where the method gets its name, the test point. And once we've tested all the different sections, we have to use the inequality symbol to help us decide which sections that we want to keep for our answer. Okay, and just another warning about what I was talking about on the last page, be sure to never put a bracket on x values that are vertical asymptotes. Otherwise, you'll create a Michigan pothole. I'm just kidding. Otherwise, Mario will lose a life. So let's go ahead and see what this is all about. With an example, we're going to solve this inequality algebraically. And as you'll see, we'll have to express our answer in interval notation. The first step is to make sure that one side of the inequality is 0. And the side that I normally make 0 is the side with the smaller power of x. So on the left-hand side, the highest power of x is 3, and on the right-hand side, the highest power of x is 2. So for that reason, I'm going to move the terms that are on the right over to the left to get x cubed minus x squared minus 6x is greater than or equal to 0. So that gets us 0 on the left-hand side. But it looks like the polynomial on the left-hand side can be factored. And so what I'd like to do is factor it. We can start with what appears to be a GCF of x. And after we take out that GCF, we get a quadratic that's going to factor as x minus 3 times x plus 2. Now, this is what I'd like to call our function f of x. What I'm going to do is kind of split off this problem a little bit, and we're going to find the zeros of the function. And we can find the zeros of the function by setting the expression equal to 0 and solving for x. And you'll probably see why I wanted the factored form version versus the standard form in this step. How many zeros are we going to get? We're going to get 3 zeros. Now, if we set the first factor equal to 0, that's one of them. The second factor equal to 0 will give us 3. And the third factor set equal to 0 will give us negative 2. So these 3 values of x are going to be important for us. The reason for that is because they're going to get plotted on a number line, thereby separating it into sections. In fact, there are 4 sections. Now, these 3 numbers are what turn the function to 0, meaning that the numbers in between these will either make the function positive or it'll make the function negative. Now, to see which sections make the function positive and which make them negative, we have to pick values from each of the sections and plug it into our function f of x. I usually go in order from left to right. Does anybody want to pick a value that would come on this or come from this part of the number line? Negative 4? Okay. So what we're going to do is we're going to test negative 4 in our function. And the version of the function that's best to use is our factored form version. Now I'm going to show you a shortcut. you don't have to grind out the arithmetic when you plug these numbers in. The most important part about the output when -4 is plugged in is whether or not it's positive or negative. Now, if we plug -4 into our first factor, that x turns into a negative number. If we plug -4 into our second factor, what kind of number do we get? Positive or negative? So if we plug -4 into here, that would give us -7. And what kind of number would we get if we plugged -4 into our third factor? Negative. So you'll see that I'm not writing out the actual numbers we get when we plug -4 into the factors. Rather, I'm just keeping track of their signs. Now, if we multiply three negative numbers together, what is the end result? Would you guys agree that the end result of three negatives is a negative if we multiply? I would agree. Now, the fact that we got a negative value using a number from this part of the number line would mean that any value from it would make the function negative. So I'm going to put a bunch of minus signs above that section. I'm going to play mind reader here, all right? A number between -2 and 0. Kevin, I'm guessing you're thinking -1. Melissa, maybe you're thinking -1 as well? How did I know that? I'm just kidding. So that's an application of probability theory right there. So we're going to move on to our next section and pick a number from it. I kind of picked it for us, -1. And let's see what kind of numbers we'd get if we plugged it into our function f of x. Okay, plugging it into x will give us a negative number for the first factor. In the second factor, we'd have -1 minus 3 giving us -4. And in our third factor, we'd have -1 plus 2 giving us +1. So what's the end result of a negative times a negative times a positive? That would be positive, wouldn't it? So this means that any value of x from this part of the number line gives us a positive result. Let me have you pick a number from 0 to 3. Anybody want to type it in the chat? A number between 0 and 3? 1.234. Okay, I love that. I can hang with it, because if you plug it into the first factor, that's a positive number. The second factor, 1.234 minus 3, will give us a negative number. And then 1.234 plus 2 will give us a positive number. Now, what is the end result of a positive times a negative times a positive? In honor of Arnold Schwarzenegger, negative. All right, then get to the chopper. Okay, folks, I'm going to have you check a number on your own from this section of the number line from 3 to infinity. All right, when you think you have the sign of your answer, you can go ahead and type it in the chat and we'll confirm it in just a minute. Did anybody happen to choose pi? I didn't. All right, I chose 4. Turns the first factor positive, the second factor positive, as well as the third factor. And the end result of a product of 3 positives is a positive. So any value of x that you choose from the section of the number line will make our function positive. So we're not quite finished, but before we move on to the next step, do you guys have any questions about this number line? So which of the two sections do we want? Do we want the negative sections or the positive sections? And that can be answered by looking at our inequality symbol. So when we define f of x, we want f of x to be greater than or equal to 0. Now what kind of numbers are greater than or equal to 0? Well, that would be our positive numbers as well as the zeros themselves. So we're going to want the plus parts of the number line. So here come a visual of our solutions, -2 to 0 and 3 to infinity, which is why we'll have to use interval notation, -2 comma 0. Anybody want to tell me why I'm bracketing -2 and 0 as well as 3? Well, it has to do with the fact that there's a bar underneath our inequality symbol. Okay, so the fact that there's a bar underneath it means that we can include these values. Now, if they were asymptotes, we would have to use parentheses no matter what. All right, so I'm going to give you one to try. I would like you to solve x minus 3 times x squared minus 4 is less than 0. Okay, as a hint, you might want to consider factoring x squared minus 4, and then you can find your zeros and number line and so on and so forth. All right, so I'm going to give you a few minutes to work on this inequality. We'll go over the answer, and then we'll take care of our last example. All right, you guys ready to go over it? So here we go. X squared minus 4 will factor as x plus 2 times x minus 2. That's the difference of two squares. And this fully factored version of the left-hand side will be our f of x. Now notice that we started out with one side being 0. If that weren't 0, then we'd have to move terms over and then, kind of reconsider our factoring strategy. But that wasn't the case, so what we're going to do now is find the zeros. And if you set each factor equal to 0, you're going to find that 3, -2, and +2 are the zeros of our function f of x. So far, so good. Let's plot these on the number line. -2, 2, and 3. So again, looks like 4 sections. I chose -3 from this part of the number line. And if you plug it into the first factor, it's negative. So is the second factor, and so is the third factor. And that all results in a negative. All right, so did you find that that section of the number line was negative? Okay, now a number I chose from -2 to +2 was 0. That would give me a negative first factor, a positive second factor, and a negative third factor, and all that results in a positive. Now there are alternating patterns in the signs, but I still recommend checking the different sections before you assume that, because there are some cases where we go from a positive back to a positive. And geometrically, that would be a case where like a polynomial is touching the x-axis versus cutting through it or crossing it. But if you pick something like f of 2.5 from that section of the number line, you're going to have a negative times a positive times a positive, and the end result would be negative. So it does appear as though there might be some alternating pattern here. Just to confirm it, did you guys get a positive section of the number line for 3 to infinity? Okay. Now, which of these do we want to keep is based on our inequality symbol. And if you look, we want f of x to be less than 0. And the kinds of numbers that are less than 0 are those that are negative. So we're going to want to keep these negative sections of the number line this time. The first section is from -infinity to -2. There's no bar underneath the inequality symbol, so parentheses, then union 2, 3, parentheses on each of those. All right, is this making sense? Is this doable? A lot of steps, but hopefully it's pretty straightforward. Okay, let's move on to our very last example of this section, last example of this month, last example of this chapter. All right, so here we're probably going to be working with a rational function, as you can tell. What's one issue coming out of the gate with this, though? Think about the steps in the test point method box. There's an issue with how this inequality is presented. It's the fact that one side is not 0, okay? So the easiest side to make 0 is probably the right-hand side. And so what I'm going to do is I'm going to subtract 2 over to the left. And when I do that, I'm going to write it as 2 over 1. Anybody have an idea as to why I wrote it as 2 over 1 versus just 2? Exactly. Yeah, so we are going to have to combine these two fractions together via subtraction. So it helps to write that number as 2 over 1 just to remind ourselves of how we subtract two fractions or add them, depending on what the number is on the right to begin with. We're going to need a common denominator, and the common denominator is going to be x plus 2. So I'm going to multiply the top and bottom of our second fraction by x plus 2. Now on the top, we'll have to distribute 2. So 2x plus 4 all over x plus 2. And when we go to subtract the numerators, let's be sure to put parentheses around the 2x plus 4. That way, we know to distribute the minus sign to both of those terms and avoid some sign errors. So the top part of our combined fraction is going to be 3x minus 5 minus 2x minus 4 all over one copy of the common denominator of x plus 2. Now combining like terms on the top, we're going to get x minus 9 all over x plus 2. This version of our left-hand side is the ideal form of f of x. Not only is it a single fraction, but there's no factoring to do on either top or bottom. Now, in the event that you get a single fraction and one of the sides might be quadratic or have a GCF, you would move on to factor. Okay, so the end goal of how you write your inequality is to have a single fraction where both the top and bottom are completely factored. And that's the case with what we have here right now. So to get our numbers on the number line, we're not only going to have to find the zeros of this rational function, but we're also going to need the VAs. Now to find the zeros, we're going to set the numerator equal to 0, and to find the VAs, we'll set the denominator equal to 0. So our numerator is x minus 9, giving us a 0 of 9, and our denominator is x plus 2, giving us a VA of negative 2. So let's put these numbers on the number line. And we're going to test values on these three different sections of the number line into our function f of x. Does anybody want to give me a value that's less than negative 2? Okay. If we plug negative 5 into our function, that's going to be a negative on top as well as a negative on bottom. And what's the end result of a negative divided by a negative? Positive, yep. So any value of x that's less than negative 2 is going to make our function positive. Anybody want to offer a value of x between negative 2 and 9 to plug into our function? Okay, we can plug in 3. And if we plug 3 into the top, that's going to give us negative 6. And if we plug 3 on the bottom, that's going to give us positive 5. And the end result of all that is negative. Negativo. Oops. I'm going to plug 10 into our function next. That'll give us positive 1 on top, and on bottom give us positive 12, and the end result of a positive divided by a positive is a positive. Now, which sections of this number line do we want? Do we want positive sections or negative sections? We want negative. Yep, and the reason for that is because we have the function being set less than or equal to 0. And the kinds of numbers that are less than or equal to 0 are those that are negative. And we do have a section that gives us negative values. That section's between -2 and 9. Now check this out. I'm going to put a bracket on 9, but I'm not going to put a bracket on -2. Anybody want to tell me why I'm not putting a bracket on -2? Okay, kind of. I put a bracket on 9 because of the equal sign. But there's a reason why I didn't put a bracket on -2. The reason for that is because -2 is a vertical asymptote. Okay, so again, -2 is a vertical asymptote, which is why I used a parenthesis instead of a bracket.